All right, let's go ahead and get started here with section 12.4. This is the cross product. Now in the previous section we did the dot product, which is a way to multiply vectors together and multiply their parallel parts together. In this one we're going to do the cross product, and this is another way to multiply vectors together, but this time we're going to multiply their perpendicular components together. All right, so let's take a look at this. So here what we have is what is called the right-hand rule. This is the right-hand rule because, well, basically it's convention and most people are right-handed, so it went with the right-hand rule. And so the idea is when you do the cross product of a vector, it gives you a third, what is technically called a pseudo-vector, but you'll maybe learn about that in another class, but it is, if you want to ask me on your own, you're fine, but we'll just consider it a vector here, though it doesn't quite have every property of a vector. What you get is a third vector that is perpendicular to both the original two vectors. And you can see that in the picture here. And the reason it's called the right-hand rule is because both a vector in this direction and a vector in this direction would be perpendicular to those two vectors. And so how do we determine which one we get when we do this? And that's where we go with the right-hand rule convention. The idea is that you take your hand, you point your fingers in the direction of your first vector, so let's pretend those are my fingers, right? And then you curl your fingers in the direction that they bend, not backwards or anything. You curl your fingers over in the direction of the second vector, and then if you hold your thumb straight out, right, like that, that's a horrible hand, it will point up in the direction that the vector you want is. So in this case, this is U crossed into V. So if I get rid of that horrible drawing, we have U fingers pointed in this direction, and then we curl our fingers over toward V, and then your thumb, you just stick your thumb straight up at a right angle to your fingers, and it's pointing upward, and that's the direction then of your vector result that results from this U cross V. All right, so pay attention to that because in a few pages we're going to you're going to use it a lot, but we're going to bring it back up in a few pages. So here is the first way to calculate it. This is U cross V, and it ultimately gives you a vector that has a magnitude. All right, this is the magnitude of U, the magnitude of U times the magnitude of V times the sine of the angle between them. And then this is a normal unit vector. So that just gives us back the direction. That means it is perpendicular to both of them. So that's a unit vector, and it is perpendicular to the plane that the other two were in. Okay, and so there is our first way to calculate it pretty simply. It's actually the coordinate independent way to calculate it, and sometimes it's very useful, and sometimes you have to go with the coordinate method of doing it, which we'll get to in a few pages. But this is independent of any coordinate system. All you need to know is the magnitude of both vectors and the angle between them, and you can do this. Here we have parallel vectors. Now notice I said that this was about multiplying vectors together where we multiplied their perpendicular parts together. Well, here, if they are parallel, they have no perpendicular parts to multiply together, and therefore you get a result of 0. So if we take this in conjunction with what we did with dot products, remember dot products, they showed us that if two vectors were dotted together and you got 0, that meant that they were perpendicular. Here, if we do a cross product of two vectors and we get 0, it's telling us that they are parallel. Okay, that's this one right there, parallel. So keep that in mind. That's very, very useful when you're trying to figure out a lot of stuff about vectors. So make sure to remember these two ideas, very important ideas. All right, so as I told you before, remember that one page, we had these same two vectors, U and V, but now this time we're doing V cross U instead of U cross V. Remember, U cross V, we pointed our fingers in the direction of U and then curled them around towards V, and then our thumb pointed upwards, and you could see that in the picture. Well, here, this time, we're doing V cross U. So this time, you start with your right hand, and you point your fingers along V, and then to curl your fingers in the direction of U, you have to actually flip your hand totally upside down so that your thumb is pointed downward, like you see here in this picture. And then you can curl your fingers over toward you. So you have to bend your fingers in the direction that you is. If you're double jointed, I get, and you can bend your fingers all the way back, don't do that. Always bend them towards your palm. And then your thumb is going to point down this time, and that is the direction of V cross U. So as you can see, unlike with dot products, when it comes to cross products, order matters, right? And essentially what you get is U cross V is going to equal negative V cross U. Okay? So order does matter. Pay attention to it. Here are some properties of cross products. Given U, V, and W are any vectors, and R and S are scalars, then you can look at these properties here. If you multiply RU crossed with SV, then it's ultimately you can multiply the two scalars together and just do U cross V alone and then multiply it on the front, because you'll ultimately end up multiplying them all together anyway. U cross V plus W, the quantity V plus W, you can actually distribute that U through and do U cross V plus U cross W. And then you can flip-flop it. But again, remember, order matters. So here we had U cross V and U cross W, but now we're doing V plus W cross U. So you end up with V cross U and W cross U. So this is going to have some negative signs associated with it between, going from 2 to 3. Here's 4, the one we just did on the previous page. V cross U equals negative U cross V. And then, of course, if we cross something with the 0 vector, see it's a bold 0, so make sure that's a vector, you get 0. And then down here at the bottom, we have the magnitude of U cross V is just going to be the magnitude of U times the magnitude of V times the magnitude of sine of theta times the magnitude of that unit vector, which is 1. That little unit vector has a length of 1. And so ultimately, the magnitude of U cross V is just UV sine theta. Okay? So, and again, very useful to be able to calculate it quickly. So here are some looks at how the basis vectors for the XYZ coordinate system, the I hat, J hat, K hat vectors work. So again, I like these with hats on them to show that they are unit vectors. So little hats, unit vector, unit vector, unit vector, unit vector. All these are unit vectors. They are the basis unit vectors that point the direction of the x-axis, the y-axis, and the z-axis. Anything along the x-axis is a scalar multiple of I vectors put together, positive or negative, and the same thing with j and k. And so what we've got here are some of these. So if you look, we have I cross, well, actually they're given to us the other way. We have j cross k, so we'll look at that one first. And so if we look, we have the vector j, that's right here in red, this vector j. You point your fingers this way and then curl them towards k, right? And when you do that, your hand is going to basically be in this kind of a situation where your fingers are like that, right? And then you're going to curl them up. Your palm is essentially pointed in the direction of the second vector, right? And so you curl your fingers up this way, and your thumb is pointed out along I. So the I unit vector is actually j cross k, or negative k cross j. And you can do the same sort of thing with all the other ones on this page, and you can see how they are related. The k unit vector is I cross j, right? I and then crossed to j that way means your thumb would be pointing up, right? Because your hand would be in this kind of an orientation, right? Like that. And so your fingers, before you did that, there like that, and then you curl your fingers over toward that j-axis, and your thumb would be pointing up. So there you go. You can do all of those that way. Try them and see if these all make sense to you. Okay, next here we have a little something that's pretty interesting, is that turns out that the magnitude of the cross product of two vectors is actually the area of the parallelogram that is defined by them. So if we rewrote, if we said this is the v vector and we transported it over here, parallel transported it over to there, and then we had the and then we had the blue vector u here, right? And we wrote it up here like that. We make a parallelogram, and the area of that parallelogram is actually just equal to the magnitude of the cross product between the two vectors. One of the things that's interesting is you can actually just say the area is the cross product between the two vectors, and then when you get into things like physics and stuff like that, then your areas that you calculate, they actually have a direction. And so areas do have a direction, and the direction that an area has, that a surface has, is perpendicular to it. So if this is perpendicular to that surface, and it's the cross product of the two, we now have a direction for an area. And that's actually going to be very important in the next section when we start talking about planes, where the area of our surfaces, of our planes, and we're going to worry about things that are perpendicular to them, okay? So pretty easy right there. You can find like I want to put in magnitude of the area of the base, okay? And this is essentially how it works. And you can see this here in this picture that if we're multiplying perpendicular parts together, we're taking u right here and multiplying it by the part of v that is perpendicular to it. And so v can actually have two components. It can have this component here, which is parallel to u. That would go to 0 in the multiplication if you multiplied that by u. And then you have this perpendicular part here. This is the part that's ultimately going to get multiplied onto u and give you that. And if you're looking at this right triangle right here, this side over here is just v sine theta. That just comes from doing, your sines and cosines from a right triangle. So basically that's what's happening when you do this cross product. It gets that. And you could do it the other way too. You could kind of flip this around and say, all right, well, I have a component of u that is perpendicular to v and a component of u that is parallel to v, like that, and say like, this is u parallel to v and this is u perpendicular to v, right? Then in this case, this will go to 0 and we'll end up with this here. We still have this, so we'll end up with u sine theta times v, right? U sine theta times v, which is ultimately the same thing as vu times sine theta or uv sine theta. So you end up getting the same thing. It really doesn't matter which one you break into components and take the perpendicular part of. It's going to work out the same either way. Okay. Here's calculating cross products using determinants. So this is when we actually have a coordinate system. This is what you do inside that coordinate system, assuming it's an orthogonal coordinate system, meaning all the unit vectors are perpendicular to each other. So this is how you do it in rectangular coordinates, the coordinates we've been working in. And so if these are the components of these, you essentially construct this matrix right here and then find its determinant. That's it. Determinant is like the magnitude of a matrix. It tells you how much, essentially what that matrix, essentially you get these, the determinant of it, it tells you how much the column vectors of the space will get changed if you operate on it with some vectors, and it tells you how much the area of the spaces get changed. But that's like the geometric interpretation of determinants. But what we're using them for here is to actually calculate this. And you can do this through the system of minors. You do I vector, this one, times, so you eliminate its column and its row, like its column and row, and you multiply it by its associated minor, u2, u3, v2, v3, like this. And then you do the next one, except you change the sign this time. So then you're going to do minus, so it goes plus, minus, get rid of those, and you do the associated minor u1, v1, u3, v3, like that, with the j associated with it. And then you come back and you, oops, not that one again, and you get rid of the k1, and you go back to a plus, so plus, minus, plus. You get rid of those, and then you have this little associated minor, so the k times u1, u2, v1, v2, like that. And actually, I shouldn't have put parentheses around those. These should be the determinants of those smaller matrices, the minors they're called, from that original matrix. And you get that, and this is how you go through and calculate it. And if you want to know how to calculate a 2x2 determinant, A, B, C, D, you do A times D minus B times C, like that. It's going to be A, D minus B, C. And that's how you calculate that. So up here it'd be U2 minus V3 minus U3 minus V2. So it's you cross them like that. And then that one is 0. If you're not comfortable with that and you don't like going through doing all of that, another trick to do is to simply rewrite the first two columns. Any 3x3 determinant you're doing, this works. It's just a little shortcut. I recommend you learn the minors way, because especially if you have to do larger and larger matrices, you need to know how to do that. You just keep breaking it down into more and more minors. But for a 3x3 matrix, you can do the determinant by simply doing this, rewriting the first two rows, and then what you will do is go through and multiply this times this times this, plus this times this times this, plus this times this times this, in those in that direction. And then you go back and you go the other diagonals, this times this and this, but you subtract these diagonals. And you can do it this way. And so it would ultimately be the 3 blue results, right? Let me see if I can write that a little better. It would be, like, let me put an equal sign here, equals, and it would be, it'd be the blue, 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 all added together, blue plus blue plus blue, whatever they turn out to be, and then minus the numbers you got going in the green direction, green, green, green. And so those would all be, you'd have to take the opposite of whatever they were. So you could do something like that, whatever it happened to be. And you'd notice you'd get I U2V3, what you're going to get right here. You're going to get I U2V3 positive. That's this one. And then you're going to get I U2V2, but in the subtraction. And so you get I U2V3, or I'm sorry, V2U3 right there, and that would be that one that you'd end up with for subtraction. Or actually, I guess, in the order I was doing it, it would be that one, but whatever. You end up getting all the same things. It's just a quick little trick. You don't have to do it that way, but either way works. Again, this is a way you should know. This little thing I did up here, if it makes sense, should be something that you can do if you just need a quick little shortcut and you need to get through it. Okay? Next, find U cross V and V cross U if U equals 2I plus J plus K and V equals 4I plus 3J plus K. So let's go ahead and try this one. You can see here they did it through the associated minors. They took I and eliminated those and had this matrix here, 1, 1, 3, 1, and that's what you see right there. And then they took and eliminated J, and they got the 2, 4, and the 1, 1, and you have the subtraction sign there. And then they go back to positive, and they do this, and they get rid of that one, and you have the 2, 1, negative 4, 3 vector right there, and it's back to being a plus. And they just went through and did those. And then as you can see here, 1 times 1 is 1, and then minus 1 times 3. So that's 1 minus 3, that's your negative 2. And then here it's 2 minus negative 4. So 2 minus negative 4, right, gives you a, well, that's, hold on, that doesn't seem right there. That should be 2 minus negative 4, sorry. There's my issue. I forgot the negative 4. And then that's going to give you a positive 6, but then we're subtracting it, so we get minus 6 right there, okay? So that's how they go through and do it. And if you wanted to try it my way, or my little shortcutty way, I'll do it real quick here. I, J, K, you should get the same ultimate answer that we got right here. And then you can see that when you switch them to V cross U instead of U cross V, it's just a sign change the whole way through. So IJK 2, negative 4, 1, 3, 1, 1, and then rewrite the first two columns, 2, negative 4, j1, 3. And so we'll come here and do this one first, and that's going to give us 1 times 1 times I plus 1 times 4 times j. So I'm just going to write a 4j because I'm thinking I'm going to run out of space here. And then we're going to have 2 times 3k, so 6k. And then minus, we're going to go the other way, 2 times 1j, so minus 2j, minus 1 times 3, so minus 3i, and then minus a negative 4, so minus negative 4k. All right, and if we go through and start putting these together, we have a 1i and a negative 3i, so that gives us the negative 2i, so that matches that right there. Then we've got a 4j and a negative 2j, so that gives us, should I have had an, oh, I'm sorry, that should have been a negative 4j. That's a negative 4 right there. That should be a negative, right? And so we have minus 4j and minus 2j, that's minus 6j hat. And then we have 6k and 4k, because that's minus negative 4k, that's a plus 10k. So you can see we got the same answer, just a different way of doing it. And you can do whichever way you're more comfortable with. But this way ultimately is what you have to do for larger and larger ones. And this, I think, only works for 3x3s. So take a look here. We have finding a vector that is perpendicular to the plane of this. So essentially, if we have 3 points, that determines a plane. What you can basically do is just simply construct two different vectors from the 3 points, and get those two vectors, do a cross product between them, and you'll get that third vector that's sticking out, that's perpendicular to both of them, right? It's perpendicular to both of them, and therefore perpendicular to the plane. And so the you can also note, after you find that perpendicular area, that the area of the triangle instead of the parallelogram is just half of the area of the parallelogram, and therefore half of the cross product of these two. You didn't have to actually pick PQ and PR. You could have picked something like RP and RQ and done the same sort of thing, and ultimately gotten the same area, and gotten, or taken half and got the same area for the triangle, and also would have ended up with a vector that was also perpendicular to that plane. Okay? So here, example 3, find the area of a triangle. So I'll do this first one, and then I'll leave the second one for you. So we have these vertices, and so we can make PQ and PR. So PQ is going to be, we'll just do P to Q, so we'll do 2 minus 1, so that's a 1i. And then we'll do 1 minus negative 1, so that's a 2j. And then we'll do negative 1 minus 0, so minus k. So that's what we have there. I don't need to write that 1. There's PQ. And then we'll do PR, right? PR is going to be negative 1 minus 1, so that's going to be negative 2i. And then we're going to have 1 minus negative 1, so another negative 1 minus negative 1 is plus 1 plus 1, so that's 2j, and then 2 minus 0, so plus 2k. So I hope I didn't make any mistakes on that, but 2 minus 1 is 1, 1 minus negative 1 is positive is 1 plus 1, negative 1, minus 0 is negative 1, and then over here, what did I have? I had negative 1 minus 1, that's negative 2, 1 minus negative 1 is plus 2, and then 2 minus 0. So I think that's okay. And then if we want to find the area of the triangle, we want 1/2 times the magnitude of PQ crossed with PR, and we would just simply do it. 1/2 times, and we'll write I, J, K, put little hats on them. And we'll write P first, so that's 1, 2, negative 1. Just writing in the components, negative 2, 2, and 2 that way. And just to save space, because I don't have a lot of room, I'm going to go ahead and do my little trick way, which is 1, -2. You should try it with the minors and see if you can get it. I really would recommend you know how to do both, but I just didn't have room to write out all these minors, which I guess I don't have to write them out. Well, yeah, well, I'm going to do this. I want to show it to you. So we have 4i, that's from this. We have 2j, -1 times -2 is 2, so 2j. And then we have 1 times 2, that's going to give us a 2k. And then we have to start subtracting. We can do minus 2j minus -2, so that's going to be plus 2i, and then minus -4, so plus 4k. Okay, and so what this then gives us, I need the magnitude of this times 1/2. Combine these together, and we've got 4i, 6i, we've got no j's left, they're gone, and we have 2k plus 6k. There we go, and we want the magnitude of that times 1/2. And then what we can do is do the magnitude of this, and the magnitude of this is just the square root of 6 squared plus 6 squared, so that's the square root of 36 plus 36 times 1/2, which just means we ultimately end up with the square root of 72, right? Square root of 72 over 2. And that should be the area of that, assuming I didn't make any mistakes anywhere. So that's what we're doing. We're doing the magnitude of that p cross, or of the two vectors cross product together. Oops. Okay, and so that's what we got there. I'll leave this next one for you to try. You're going to do the exact same thing that I just did here, but you're going to find, instead of taking the magnitude of it, right, you're finding a unit vector perpendicular to the plane. You're going to do PQ crossed with PR, or however you take them. It could be RQ, RP, cross those two together or something. But do PQ cross PR, and then when you find it, you need to divide it by the magnitude of PQ cross PR. So give that one a try, work your way through it, and see if you can get an answer for it there. Okay, and then that should be a unit vector for you that is perpendicular. This numerator here gives you a vector perpendicular to the plane that those are all in, and then dividing it by its own magnitude gives it a length of 1 and therefore makes it into a unit vector. All right, here is an example of something from physics called torque. Torque is very similar to work in how it looks. So if you remember, work was F dot D, and it was a scalar, and it ultimately had a unit of a Newton meter, right, which equaled what I said was a joule. Here we have something called torque. Usually the symbol for that, a lot of times if you're in physics and stuff, is a tau, but it's a vector, and this time it's a force crossed with a lever arm, which in this case we're calling r, but it's still a length. It's a force times a length. Just like here, we had a force times a length. But the difference is that in the work force times length, they were dot product. It was a dot product, and it multiplied the force times the displacement, and it did it with a dot product where it multiplied the parallel parts together and created a scalar. In this one, we are multiplying a force and a length together, but we're doing it with the cross product, and therefore we are multiplying the perpendicular components, right? This was parallel. Here we're multiplying the perpendicular components together and getting something different. We're getting another vector this time, or a vector if I'm putting my quotey fingers up. And notice again, we have a force, which is a Newton, and a length, which is a meter. So we get a Newton meter, but this one is not a joule. This joule up here is for a scalar quantity, a scalar dimension. So therefore, this is not a joule. It is just a Newton meter. So they are differentiated that way, in case you noticed the kind of the similarities here. So the idea with torque is you have a pivot point, that would be here. You have a lever arm right here, which is a vector pointed out away from the pivot point, and then you can apply a force a certain distance out. If I applied that same force in over here, right, my lever arm would effectively be reduced to this right here instead of the big longer one, and then when we multiply them together, we would get a smaller overall torque. If you want an example of this, go find a door. We put the door handles on the opposite side of where the doors rotate, where the pins are, and therefore it makes it easier to open the door. So if you have a doorway here, you put the door handle here, and you put the pivot points, the pins, on this opposite side. So when you push, you're applying a force, and then there's this length right here is your R, your lever arm, and it gives you the maximum force. If you want to try applying the same force, if you want to apply, I had to erase something that was there before. If you want to try this, go apply the same force, or see how much extra force you have to apply by pushing over here near the pins. Even if you push with the same force, you have to push with quite a bit bigger force, because your R, your lever arm, gets shrunk down to being very small, and it's a lot harder to open it. Same thing with using wrenches and stuff. Okay, so this is the basic idea of torque. It's a vector quantity that describes this, and of course is perpendicular. I'm on the erase. Is perpendicular to the original 2. All right, and we can do this with FR sine theta, and then that's that unit vector, that unit normal. And then here is just our magnitude, where we don't have any direction. We're just taking the magnitudes of them. Okay? So that's how you can go through and calculate torque. So let's try one here. So here, in a quick little example, you've got the magnitude of torque exerted by F at P is 56.4. So here you have an answer already. I want you to go through and try and do it. I'll give you a little hint here. This is your force vector, obviously. And then this is your R vector, okay? And this will be your pivot point right there at P. So try calculating it and see if you can get this answer that's right here. Now, they have it in foot-pounds. I did Newton meters, but they are ultimately the same thing. It's just this is in, not in SI units. Newton meter is SI units, so sorry about that. All right, let's try one. Right here, you can see one fully worked out. Actually, that's the same one. They're working it out for you right there. I'm sorry, I didn't even realize that. I was thinking it was another example I had to go through, but nope, same one. So go through and you can see right there, after you tried that one, take a look here, you got the whole answer. All right, taking a look here, what we have is what is called the triple scalar product, and this gives us the volume of a parallel pipe head, which, if you think about this, if we looked at this and we did U cross V, so we did U crossed into V, that would give us this area of this parallelogram, which is the base of it, right? And then what we're doing is multiplying this up through W, multiplying it up through, adding it all the way up through. That's what multiplication is, a bunch of repeated addition, right? We're multiplying it up through there and ultimately getting the total volume that is there. And it doesn't really matter that it's skewed off to the side. All that we really care about is the height. And if you want to think about it, pretend we had a stack of books, right? Here's our books. And we had a stack of books like this. And then, I don't know, 3 books. I don't want to draw a bunch of them, maybe 4. So let's say we had 4 books stacked like this. And these books would have a certain height to them, h, right? They have a height h to them. If I take those books, same exact books, and I push them such that they end up like this, such that, see if I can draw this, that they end up skewed off to the side. Whew. I don't know how I'm doing here, but we end up doing the same 4 books, but pushed off to the side like this. right? So they're now slanted this way, right? So before they were stacked straight up, now they're stacked at an angle. They're still going to have the same height, aren't they? It's still the same height as you had before you did that, and it's still the same volume that you had before that. So instead, instead of even thinking about these books, let's take it down to the individual pieces of paper. Start with a stack of papers like this, right? Take that stack of papers and skew it off to the side, but it's still that stack of papers, right? Where this was our stack of papers. We still end up with the exact same height, okay? We just have them skewed off to the side like this. The height doesn't change. And so as long as we can find this height right here and multiply it by the area of that base, which stays the same the whole way, we have the volume of it. Well, how do we do that? We do that with cross products, because that is multiplying perpendicular parts together. The perpendicular part up here is not the perpendicular part, it's going to be the parallel part, because when we take the cross product of u and v, we're going to get a vector that points perpendicular to that. And then if we dot product it, right, so this gives us a vector that's parallel to w, and then that's perpendicular to uv, perpendicular to that base plane. If we then dot it with w, we're multiplying it by the part of w that is parallel to it, and that's that vertical component right there. Okay, it's this vertical component of w right there, and it eliminates this component, this component of w. It's gone, and we end up with the area of the base times the height, where w cosine theta is the height of the base. All right, I made a giant mess out of that, so I'll make it look a little cleaner. Okay, so this is finding the area of the base, and this is then dot producting on to get the height. All right, and that's how you find this, okay? And so you can go through and do that. And so the absolute value of that, which you're doing a dot product, so you're really just getting a number in the end anyway, not a vector, is the area or the volume of that whole thing. Here is a quick way you can calculate the scalar triple product. If you think about it, when you do the dot product, remember when we did u cross v, right? When we did u cross v, it was I, j, k, and then u1, u2, u3, v1, v2, v3. And that's what we did to get this cross product, right? And then, of course, in the normal direction. But let's pretend we're only looking at this absolute value here for the moment. Although, well, no, I don't want to do that. We'll put the n back in, okay? N vector, so the normal vector. So when I did this, my I component was composed of this part right here, right? Into a little minor. My j was composed of what? Was composed of this part right here. This was the j part. And then the k part was composed of these right here, right? Well, if you look down here, I would be dotting u1 onto the result of this minor. And then I'd be dotting j, or u2, this one right here, onto the result of, gosh, that got messy. I got to get rid of those. I'd be multiplying u onto this minor over here that I would have gotten, that would have been the j component. And then I'd be multiplying u3, right? I'd be multiplying u3 by this minor, which would have been the k component, right? That would have been this k component up here. So essentially we can skip a step, just figure out and draw this matrix here, find its magnitude, and we'd be done. So u cross v dot w. So if you forget this, though, you can always just do u cross v the long way, get a result, and then dot it with w. Either way is going to work. So this is just kind of a little shortcut for you. Here is a little example for you to read through. This video is getting kind of long, so I'm not going to spend a lot of time on it, but you're just finding a volume like we did before, but you're using this. I recommend that you also try doing this with finding with actually finding the cross product first and then dotting it on W and see if you get the same answer. So try it both ways. And then that's pretty much it for this video. So hopefully this makes sense to you. If you have any questions about it or anything, then just, we'll have to take care of it when we meet. All right, that's it. Thanks a lot. Bye.